With each fascinating picture captured by the James Webb Space Telescope, it continues to gather thought from various corners of the universe, including planets within our own planetary system. A year earlier, we considered our most important brief glance at pictures showing the Carina Cloud, Stephan's Quintet, and strikingly, the entrancing deep field image. This particular picture obviously depicts different galaxies relaxing into the monstrous spread of the universe, fulfilling the assumption made. The James Webb Space Telescope hasn't stopped at a labyrinth. It has actually uncovered objects that challenge broad cosmological considerations. These stunning revelations are now classified as universe breakers by cosmologists, puzzling mainstream scientists with their ability to challenge existing ideas. The reasons for these exposures remain cloaked in mystery, throwing our theories and hypotheses into disarray. So, what's the latest scoop from the James Webb Telescope? What exceptional new discoveries has it uncovered that were previously unknown to us? Join us as we dive into the revelations of how the James Webb Telescope has presented evidence suggesting the presence of another universe, challenging the standard understanding of the Big Bang. Our universe, as we've long seen, emerged from a hotter, denser state via a theory known as the Hot Big Bang. This idea, a colossal scientific achievement over the past century, gained overwhelming support during the 1960s with the discovery of the cosmic microwave background, CMB, a remnant from the early hot and dense state. Over time, the Big Bang theory has remained the dominant explanation for the universe's origins. However, new and critical observations have led cosmologists and astrophysicists to question both the ongoing expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain momentum, focusing on the enduring nature of the Big Bang theory. According to the general view, the description of the universe's beginning involves a smaller, denser universe in the distant past. The presence of radiation, like photons, shows that the universe was hotter at its start and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels arrive at a point where a singularity could form and the conventional laws of physics break down, around 10 to the power of minus 43 seconds. In such a short span, small distances, brief time scales, and high energy levels challenge our understanding. Rewinding the vast clock to the speculative 0 point, if the universe began hot and dense, it would have expanded and cooled, producing a vast number of particles and antiparticles, with excess particles annihilated by radiation. As temperatures decreased, the breakdown of the electroweak and Higgs symmetries led to the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The combination of protons and neutrons led to the formation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions underwent development due to radiation pressure, followed by gravitational collapse, leading to the formation of large-scale structures. About 380,000 years after the Big Bang, the universe cooled enough for stable neutral atoms to form, marking a key point where photons decoupled and their frequencies stretched as the universe expanded. The discovery of the cosmic microwave background decades ago cemented the Big Bang theory as the most supported explanation for the universe's creation. The debate, Big Bang versus steady-state theory. While most cosmologists and astrophysicists embrace the Big Bang theory, staunch defenders of the steady-state theory, like Fred Hoyle, continue to support increasingly unlikely ideas, only to face defeat against overwhelming evidence. The proof presented was unequivocal. It wasn't fading starlight or reflected heat from dust. The cosmic glow showed a stunning consistency, appearing as an ideal black body, yet had no connection to known objects in the universe. Despite this, Hoyle and his followers continued to block scientific progress by supporting these misguided ideas. Meanwhile, the fields of space science and cosmology underwent tremendous advancements from the 1960s through the 2000s, with cosmology experiencing particularly striking shifts. We mapped the vast universe and described its structure on an enormous scale, studied the development, evolution, and dynamic interactions of galaxies and their stellar populations. However, despite these advances, we encountered anomalies that challenged explanations within the framework of the Big Bang Theory. Observations uncovered discrepancies, such as the lack of exotic relics predicted by the theory, like magnetic monopoles or particles from grand unification. The universe we observe today seems to require forces beyond our current understanding, but these remain elusive. At its inception, the universe required an exact expansion rate to balance the total energy density, an achievement that the Big Bang Theory struggles to justify. This led to neither firm equilibrium nor enough time for energy exchange across vast regions of space, given the universe's immensity and its expansion over time. These anomalies present significant challenges for cosmology and mainstream scientists alike. The inflationary model and its challenges. While existing theories fail to account for observed anomalies, two approaches have emerged: refine existing theories or consider alternative explanations. The theory of inflation emerged as the most promising framework to extend the Big Bang model. Inflation suggests a period of rapid expansion, smoothing out the universe and imparting uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. Inflation's predictions align with observed patterns, lending support to its validity. While alternative theories exist, inflation's scientific strength remains unmatched. However, despite past contributions to general relativity and singularities, Roger Penrose's work, alongside his collaboration with Stephen Hawking, failed to match the progress of inflation in explaining the universe's earliest moments. Recently, there has been a concerted effort to undermine the validity of inflation theory, promoting formal cyclic cosmology instead. However, this theory is inherently flawed from a scientific standpoint. The key difference lies in their predictions. Conformal cyclic cosmology proposes that remnants from a universe preceding the Big Bang are etched in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflation theory maintains that the end of inflation and the hot Big Bang are causally disconnected from any pre-Big Bang region. Every aspect of our universe displays remarkable qualities, suggesting that we should rely on the universe itself to reveal what is true, rather than merely depending on theoretical models. James Webb Telescope's astonishing discoveries. Space scientists quickly noticed inconsistencies in the images sent back by the James Webb Space Telescope starting in 2022. These discoveries may require a reassessment of key aspects of the universe's origins and evolution. One significant revelation made by the Webb telescope was the presence of fully formed galaxies much earlier than anticipated by the standard model of cosmology. This phenomenon challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by galaxies. Such discoveries disrupt our understanding, similar to encountering grandparents described as children in a story. Moreover, recent evidence has revealed inconsistencies within the primary theories of the universe, such as the ongoing error in determining the Hubble constant, which persists despite improvements in data accuracy and collection methods. Additionally, new data from the Webb telescope intensifies existing challenges to the current cosmological model. These issues highlight flaws within the model, prompting questions among space scientists and physicists. While the model has undergone adjustments over the years to align with emerging data, some argue that these modifications have been overly accommodating. Consequently, there is growing recognition that a shift in perspective may be necessary, potentially reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe during the 1920s. Subsequent discoveries, such as the cosmic microwave background radiation in 1964, confirmed the theory of the universe's origins, portraying the early universe as a hot, dense soup of subatomic particles that steadily cooled over time. Reevaluating cosmology in light of new evidence. Achieving the current level of precision in cosmological understanding has required theoretical extrapolation beyond observational data. The concept of eternal inflation, proposed in 1981, was introduced to resolve anomalies in earlier Big Bang models, further emphasizing the dynamic nature of cosmological theory. According to this model, the early universe underwent rapid, exceptional expansion for a brief period following the Big Bang. While certain issues are addressed by this idea, new challenges emerge, particularly given the widespread belief in the existence of a single universe. Perhaps there are countless others beyond our observational reach. Specific observable anomalies, such as hypersingularities within black holes, find support through indirect evidence. The surprising discovery of such anomalies raises more questions than answers. If our understanding of the universe's origin and structure is indeed incomplete, the findings from the James Webb Space Telescope may be pointing us toward a new frontier in cosmology. This could potentially force a major revision in our current models, or even suggest entirely new paradigms for how the universe operates on both the largest and smallest scales. One of the most striking implications of these discoveries is the possibility of multiple universes or alternate realities. While this may sound like science fiction, some researchers are beginning to entertain the idea that our universe is not unique. Instead, it could be one of many, existing within a vast multiverse where the laws of physics and fundamental constants vary from one universe to another. The presence of objects or phenomena that defy current theories could indicate that we are not observing the full breadth of the cosmos, but only a small, localized region. Moreover, the James Webb Telescope's observations of galaxies appearing earlier than previously predicted suggest that the timeline of cosmic evolution could be far more complicated than we once thought. The detection of galaxies forming and evolving when the universe was only a few 100 million years old challenges the accepted theory that galaxy formation was a slow, gradual process that took billions of years to unfold. This discovery points to the possibility that the early universe was more complex, perhaps with processes or mechanisms that are yet to be fully understood. These revelations could also offer a new perspective on the so-called dark matter and dark energy that make up most of the universe's mass and energy content, but remain largely invisible to our instruments. If galaxies and other cosmic structures were forming earlier than expected, it might indicate that dark matter and dark energy play an even more significant role in the early universe than we had previously realized. Toward a new cosmology. As we move forward, the findings from the James Webb Space Telescope offer both challenges and opportunities. They suggest that the universe is far more mysterious and complex than we imagined. The new data may force scientists to reevaluate long-held assumptions about the Big Bang, the expansion of the universe, and the nature of space-time itself. This is a time of tremendous uncertainty, but it is also a time of immense possibility. Ultimately, the work of the James Webb Space Telescope may lead us to a more complete understanding of the universe, one that integrates these new discoveries with existing knowledge and provides a more comprehensive theory of cosmology. Whether this means refining the current models or adopting an entirely new framework for understanding the universe, the future of cosmology looks brighter than ever. The questions raised by Webb's discoveries are only the beginning, and the answers, though still unknown, hold the promise of reshaping our view of the cosmos in ways we have yet to imagine.